basically in 1994, there was an SPE gas condensate forum. And I think it was in 1992. Even Fevang started his PhD with me at NTH. And what I gave him, I said, well, as of today, nobody knows what the hell is going on, which was a correct assessment of the situation. And a lot of people were talking this and talking that, and gas condensates became much more of interest. Okay, value of gas had gone up, condensate value, et cetera, et cetera. So it was a lot more interesting. I said, I think I basically said, please remove the fog. And that's what he proceeded to do. Now, at this SB forum, this was a 1-week deal. All of the kind of famous people in gas condensate, all of, everybody was there. It was in a beautiful resort in Austria. I can't remember exactly the name of it. It was a 1-week deal. There were no papers, but there were some poster presentations. And I remember that by 1994, they even had made the first major kind of identifying the first major breakthrough of what was going on. Okay, he had found this 3-region model, and we wanted to present that. And so when I applied to be part of the forum, it was like only 100 people maximum. They said no to Even. They said yes to me, and they said no to Even because nobody knew Fevang. And it was overbooked. So I wrote and I said, well, take him instead of me. Okay, I give my spot to him. I don't need to come, but you want to hear what he has to say. And so back and forth, and so they ended up letting us both come. Now, at that point, Fevang had come up with this, and he presented a poster at that, the 3-region model of condensate blockage. Okay, and what he had found and what he showed is that you have this region 1, which is the steady state flow region. It follows the Evinger-Muscat equations. Okay, and then you had this region 2 where you had condensate accumulation but no condensate flow, and you had a very limited reduction in KRG. And then, of course, region 3 is region 3, single phase flow. Okay. And what he had shown is that the only thing you needed to know to model region 1 accurately, and that's where 95% of the blockage was coming from. At that point, with the only requirement to get this right was you needed to know the producing gas oil ratio, or as in condensate, the producing oil gas ratio. Okay. So you're below the bottom mole flowing pressure. The bottom mole flowing pressure is below the dew point. The producing oil gas ratio is not, let's say it's region 3. It's not the initial. Okay, it's not 50 barrels per million. It's 47. You need to know 47.
How did you figure out these 3 regions? Was there a set of lab experiments, or was it all coming from?
No, so he did everything with modeling, with reservoir simulation models. So he went he kind of did a deep dive into looking at the near well region. He saw that the flowing compositions, the flowing GOR was constant. You actually take cell to cell and you could calculate the flowing GOR. You saw that it was completely constant out to a certain point. The flowing CGR or the flowing GOR, flowing composition, was constant in that region. And then it basically radically went quickly to this region 2, where you didn't have mobility of the oil and you had this slightly reduced. So he saw it from inside the model. And if you knew this right, then you could get exactly the pressure drop, region 1, region 2, region 3. You could get the entire pressure drop. You could compute exactly this, the shape of this mobility of gas. So for a given producing gas oil ratio, which let's say is less than the producing oil gas ratio initial, so you could immediately identify, of course, this region 2. You immediately knew P star. And in this range here, you had a slight reduction. You know, if this is our dry gas, I'm just going to draw that in here, our dry gas. So you basically got this, the mobility here. This went slightly under the dry gas because the KRG under there. And then as soon as you reach P star, then this thing dropped off the wall. And in this entire region 1, the theory of having your muscat was being applied. You basically knew the producing oil gas ratio. You could compute from that, you could compute the KG-KO ratio. From the KG-KO ratio, you could get the KRG, and then you had the function. So,
question.
Yeah.
On the, can you define this P star?
So the P star is basically the dew point of the flowing mixture.
Could maybe show it on the monthly article figure.
Of the producing CDR. Yeah, so it's just the pressure right here, whatever the pressure is. Because coming in from region 2 was gas only flow. It's saturated. So, and what flows into region 1 flows out of region 1. So basically it's saturated at this point, and that, yeah, so you basically knew the boundaries, the pressure boundaries, and for a given producing oil gas ratio. And what the Odell-Miller, if you say it's steady state throughout the entire reservoir, then that would be this. That was the Odell-Miller. Region 1, no region 2. Okay? And you can see the loss of area, the loss of mobility in a big chunk. Because what they were doing, they were assuming that the producing oil gas ratio was equal to RSI. The dew point at RSI is actual PDI, and so the blockage started way out there and went the entire reservoir. So that was the problem. And but the problem we had, the problem we had when we went to this conference, we knew that this was right if you only knew the producing oil gas ratio. But there was no way to predict that from a material balance or anything else. Still today, there's no way to predict what's the RP for a given state of reservoir pressure. So that was not there. That method was not there. So the problem was that we didn't know how to get that number.
Can you repeat that? What's the problem?
If you took from the model only the producing oil gas ratio, then you could compute this entire rate versus PWF. So whatever, if you're producing OGR was 47 barrels per million, the flowing bottom oil pressure was 2,500 pounds, we could take it from 2,500 pounds, we could compute exactly the rate within 3 or 4 or 5%. You get the exact area. But we needed to know it was 47 barrels per million and not 50, and not 45 and not 42. And you didn't know what that was. So that was the problem.
Sorry, can you, maybe later, can you go back to the paper which you sent on condensate blockage? Because here it says that this time the condensate gas ratio is decreasing and KRG is increasing. Isn't it the other way around? When we go below the dew point, KRG is decreasing? Or am I getting something wrong?
Yeah, no, we're going to come back to that, but the KRG in region 1 gets better as you deplete as the producing CGR decreases. That's what we're going to be talking about today. The thing is that the KRG in region 1 depends on two things. It's the rock curve and how rich the fluid is. So if during depletion the fluid's becoming leaner, then the KRG will in fact start increasing. The amount of the blockage impact of reduced KRG is becoming less. So the worst condensate blockage when you have the richest fluid flowing. Okay, so anyway, this was 1994, and this was kind of like, this was a major thing for us because, it's great to have the theory, but how do you use it? That was the problem. That was the problem. And the only kind of modeling that we had done was very fine gridded models of a radial grid like Fussell did in 73. We did very fine gridded modeling. We were getting the right answer. And, we just, if you have to run the model anyway, why do you need the theory? So that was, when we went there, Avon's work gave an explanation, this 3-region, but how to use it, that was the big question. So at this meeting, I think it was 5 days, and maybe the middle of the week or the second day or something, there was a paper by Amoco. I don't remember who presented it, but it wasn't Fussell, but it was somebody from Amoco. And what they did is they had built a solution. Their solution was to run hundreds, if not many hundreds or maybe thousands of simulations okay? And then calculate what skin term they needed in their well index of the model. They wanted to run full field models, okay? They wanted to run full field models. So they basically built a full field model, large coarse grid scale model, okay? That was exactly like their detailed radial model. And then they ran the radial model with different rates, different drawdowns, different levels of depletion, different fluid systems, et cetera, et cetera, et cetera. And then they calculated for every run at every time the blockage skin needed in the coarse grid model to give the same rate, to give the right rate. So they had this multi-dimensional table of blockage in their reservoir simulator because they had built their own reservoir simulator, okay? And it was a function of rate, flowing bottom hole pressure, of producing oil gas ratio. It had like 5 variables. Multi-dimensional. That was their solution. And then what they were doing is to show off how good the solution was, they plotted, of course, rate versus time, gas rate versus time. That was from their single well model, detailed grid. So that was the answer. And then they came in with their the full field model, like that, and they, like that. Okay, very impressive. But it was like yesterday. But then they also, on the same figure, just by chance, they plotted so this is rate, these are rates. They plotted from the single well model, actually they used producing gas oil ratio, so I'll show it in producing gas oil ratio. And they showed full field model, producing gas oil ratio. And the answer here was like this. When you see the GR going up, you see the CGR going down, right? So it looked like that. And then they also plotted this GOR from the full field model. And they showed about 10 of these. They were mainly having us look at the rates to be impressed with the solution. And like after 5 of the 10 figures, they showed this, and every one of them we saw the producing GOR from the full field model was giving the right producing GOR from the fine grid model. It was saying that the coarse grid model had enough refinement to get this to describe the region 2 to give us the right GOR. And like I stood up, I couldn't sit, and I'm sure Fevang had exactly the same thing going through his mind, because this GOR match between the full field model and the single well model meant that in the full field model you could take the GOR, implement the 3 region model, and compute the well PI immediately. So this match between these two here meant that the full field model plus the 3 region Fevang model, you could get exactly the relationship between rate and bottom hole flowing pressure. And it was champagne and caviar that night. And that basically is what brought us to what we'll be talking about tomorrow. Sing's going to discuss the so-called GPP option in Eclipse 100, Eclipse 300, the treatment of this condensate blockage within a full field model without any grid refinement to handle the region 1. You treat the region 1 purely through this model. And then the simulator is basically taking care of the region 2 with its numerical gridding.
But if you're using the simulator to get the RP or the CGR, then isn't it also giving you the rate versus time?
No, it gives you, if you don't, the thing is, they got the rate right because they were using these dynamic blockage skins in the model. If they took away the blockage skin table, then the full field model would have a plateau way longer than the single well model. So the reason they got it right, the rate time part, was because they had this dynamic multi-dimensional blockage skin that they had to take forever to build, and for every new.
But the GOR, how would it look if you didn't have the skin?
No effect.
No effect.
No effect at all.
Yeah, so that's the secret. So
Yeah,
no effect.
Even if they didn't have the skin, you get the same GOR. And with that
Exactly.
GOR,
With or without the skin, in fact, I think they even showed cases before they used the blockage. They showed, so as long as it was on the same plateau, you got the same GOR profile. But of course, if the plateau goes much longer, then the GOR breaks because one's depleting faster than the other. So, yeah. So this was.
So you're dynamically using the predicted CGR to give you the rate, and then you can get the new CGR.
No, the CGR comes from the grid, the course grid model. Yeah, you have, that's input to the 3 region model. So the treatment of region 1, you have to have the right GOR, producing GOR.
Yeah.
That you get from the full field model with or without block.
It's almost as if you were taking the GOR from the model and using that GOR to pseudo calculate this skin automatically for every time step.
That's exactly what it did.
Exactly what it is. Yeah.
That's right.
So like.
But you have to calculate the CGR for each time.
Yeah, but you have it from the model. That comes
Yeah, but that's
better.
what I'm saying is that it's.
Yeah. So the implementation.
How do you get the entire curve?
Yeah. So you basically have to, in the simulator, every time step, calculate this red curve.
Yeah.
That's what's being done with the GPP option. And so basically in 1995, this paper was written, giving not only the 3 region model, but the fact that you could use the full field model to get the GOR, everything. So that's this paper here, which was Fevang. He received the Cedric Ferguson medal for the best paper by someone under the age of 32 or something. And then it was voted the best SB Reservoir Engineering paper that year, 1995, because it really did lift the fog. The industry, everybody was kind of like off. So this really did lift the fog. So he received all of the awards that he should have. And so let's see here. Yeah. So really, there's not been anything. I mean, this is basically accepted as being the way to treat and properly model the condensate blockage problem. Now, I will say this: in 1994 at the forum, there was an extra topic, and that was, what are the relative permeabilities that should be used? Okay. Relative permeabilities was a very hot topic in this conference. And there was two items that were being discussed. The one was the importance of the residual oil saturation. The second was whether it should be imbibition or drainage process. And probably the newest thing, these other were discussions that continued, but the newest was that the capillary number improvement. Capillary number improvement of both KRG and KRO due to high velocities. Near the well for a vertical unstimulated well. Now, the work that Fevang was doing in his PhD thesis answered both of these issues here. Okay? So basically, what Fevang's work showed was that the SOR itself had no direct impact on the blockage. Okay? So we basically went there preaching without anybody listening too much, but was of little impact or no direct impact. And on the second question, it was simply that the process that you wanted to measure relative permeabilities with, it could be imbibition or drainage, it didn't really matter. But what was most important is that you needed to use a steady state flow test. Steady state flow test. And then if you did steady state flow test, you could then study whether imbibition, drainage, hysteresis had any impact on the steady state flow relative permeability. Okay, and that was done years later, but the most important thing was that it needed to be steady state and that the SOR had really no effect directly on the blockage. Now, the people working on the capillary number was two groups. It was the Shell group and it was the University of Delft, both out of the Netherlands. And Shell, I think it might have been Tom Schulte, I don't remember, presented some of their results on the measurements they were making, and University of Delft was making measurements as well. And they were showing data that said the magnitude of improvement of KRG was significant at high enough capillary numbers. So they basically presented results and said that it can't be ignored. So So in the paper, 1995 paper, we actually had some time to at least do basic calculations of the impact of capillary number on relative permeability on this region 1 blockage effect. So we actually have some discussion of that in the paper. So,
Here, the SOR is the same as SOC, the critical.
yeah, SOR and SOC is the same thing. Basically, it's where KRO goes from 0 to epsilon, where it goes non-zero.
Can you please elaborate what does it mean SOR had little not direct impact? Because I mean, we always thought that the capillary number is reducing the SOR, and this compromises a significant part of improving the relative permeability. So you go from some base SOR down to 0, some infinite number of capillary number, and this impact was always for us very important.
Yeah.
Now
So-
I'm kind of challenged by what does this SOR at least what means.
Yeah, so what you're saying is that, you had been thinking or observing that SOR or SOC and can be important to the blockage effect. So we're gonna be talking about that a little bit today and quite a bit tomorrow when we talk about the lab experiments. Everybody at that conference was saying the same thing. SOR is very important to blockage. Everybody. And we were basically saying it didn't matter. And so, but there was a reason why everybody thought it mattered. It's not like, okay, but it was not an experimental reason. Okay?
Intuitively, you kind of think it matters.
You think it matters, but it was not an experimental measurement in the lab that said, the reason people were saying that SOR was important was the following. Everybody was doing modeling at that point. All they did was model. And then the modelers saw that, if we change the SOR in our model through an analytical Corey type equation, then you saw a big effect on condensate blockage from the simulator, fine grit simulator. Everybody was doing that. Everybody was getting the same results. And everybody was sending to their laboratories the need to measure residual oil saturation very accurately. Okay? But what we showed is that region 1 relative permeability behavior is, I'm calling it far removed from critical oil saturation because it is where you have oil mobility. Okay? And the reason why people think yourself, there's nothing wrong with it, but people were thinking that, argued that SOR is important, is because they were using these Corey type equations KRG, KRO, which basically is, kind of 1 minus SOR, what I call normalized to some power, NG, and this is SO normalized to a power SO, power NO. So NG, could range from 2 to 4, NO likewise 2 to 4, it depends on pore size distribution, blah, blah, blah. But this SON is like SO minus SOR over 1 minus SOR minus SWC. I don't remember. It should be something like that, I think. If
Just normalizing the
Huh?
x-axis. It's just normalizing the x-axis to go from 0 to 1.
so you basically go from 0 to 1 from the connate water to the residual oil saturation. Okay. Okay. And because of this so what basically what we were saying, which is what Evinger and Muscat said, so they're the ones who said it first, they said that in region 1, the only relative permeability relationship that matters for gas condensates is KRG as a function of KRG over KRO. Okay? That's all that matters. There is no saturation above. You don't see oil saturation there. Okay? And so what we did in the paper, and what happened with this something like that. If this was SOR, nothing else changes, the exponential. If you just change SOR in the equation, 20%, and you change it to 10%, what happened is that I don't even know how it's going to look. I think it goes up. So this is maybe SOC 10%. And 30% maybe down here. Something like that. And the range of interest of these here is basically, it depends how rich your fluid is, but the realistic range of interest is, for any gas condensate, is basically here. Okay, this is for a very rich gas condensate. This is for a leaner gas condensate initially. So the point is that you're getting KRG values that are changing like this, just with a simple parametric change in the equation. So yes, it's going to have an impact, if that's what you mean by SOC. It has nothing to do with the physical value of the residual oil saturation. And so
I guess if you had different SORs that gave you the same KRG, KRO versus KRG.
Yeah.
So basically, if you change the exponent to give you the same curve, then the SOR wouldn't have any impact.
Yeah, so that's what we do in the paper. We show that. You know, it's very, the simplest way to do it is that you say you've got your table of SO that's your laboratory. See, if you bring in the laboratory and you bring in these measurements like that, okay? Then you calculate your KRG over KRO. Okay. So what we did is that we said, okay, this is our rel per measurement. But what we say is that the oil saturation, I'm not even going to look at that table. Okay? You know, maybe I can put any set of physically meaningful oil saturations here in the right column. Okay? Any. And you have identical relationship KRG to KGKO. So I can pick any of these sets of saturations that you can have an SOC of 0, 10%, 35%, and I can manipulate those saturations from what was actually measured or what they thought they measured, or maybe they didn't measure. It doesn't matter. What matters is how KRG varies as you change the mixture flowing through the rock, defined by KGKO. So we basically show that you can, you know, in the model, you'll get different levels of saturation near the wellbore, but it has no effect at all, zero effect on the blockage magnitude. As long as you keep what the laboratory measures. And what you want the laboratory to measure is basically these, you basically set up the range from the minimum value of interest to the maximum value of interest, and you measure KRG and KRO in that range. That's all you need to measure. You don't need any saturations at all. You need to find out what the actual, what the actual data looks like, and the actual data might look like this. Okay? That's the relationship you need to know, and not the residual saturation at all. The residual oil saturation is occurring way out to the right, no interest at all. So basically what we say is that you go in and you make measurements of, steady state flow tests in the range of interest of this 0.1 to 100, 4 or 5 mixtures covering that range, measure the KRG, and you're done in terms of modeling region 1. Basically. So we're going to come back to this, revisit this in detail, in particular tomorrow when I talk about the laboratory experimental methods that are recommended, et cetera, et cetera. We'll come back to this, but the relative permeability was also very cloudy in 1994. There was a lot of misconceptions about whether it was drainage or imbibition process, the importance of the residual oil saturation, and what was important was this capillary number dependency, which really is only important for unstimulated vertical wells, where the velocities really get high near the wellbore. If you have a hydraulically fractured well, the flow velocities into the hydraulic fracture are 1 to 2 orders of magnitude lower. And We'll come back to this in more and more detail. Hopefully it'll become clear by the end of the week. Okay.